Wow, I'm a bit overwhelmed, I have to say, by the turnout and also extremely honored by receiving this important medal. It was a really pleasant surprise for me to be nominated in the first place. And the opportunity to give this medal lecture prompted me to look back over my career, more than 30 years of research on and off on this topic, because I'm actually approaching retirement faster than the AMOG is approaching a tipping point. So it's a bit of an emotional thing for me to now look back over what I have done in all these decades, and also, of course, an opportunity to thank several people, including my supervisor as a postdoc after I had come from my PhD in New Zealand was Jürgen Willebrand at the Institute of Meereskunde in Kiel, and he actually put me onto this topic of Atlantic overturning circulation stability. And he also was a great role model for me as a theoretical oceanographer. And I also want to thank, of course, many people that worked together at the Potsdam Institute later with me on this topic, like Andrei Ganopolsky, Marisa Montoya, Anders Levermann, Kirsten Zickfeld, Till Kuhlbrot, Matthias Hofmann, Georg Feulner, Alexa Griesel, Alex Robinson, Levke Cesar, who's sitting in the first row here, and actually many further people that I can't list, international colleagues that I published together, like Matt England, Mike Mann, Richard Alley, and others. I want to start with a short introduction. What's the AMOG compared to the Gulf Stream? And then I have two main topics. Is the AMOG slowing down? And what about that tipping point? So let me start with the introduction. The Gulf Stream was first mapped by Benjamin Franklin in 1769. He was the postmaster for the American colonies of Britain and was wondering why the postal ships took much longer to come from Britain than to go back to Britain from the US. And he talked to some fishermen, and they knew about the Gulf Stream. And the Gulf Stream is often confused, but it's not the same as the AMOG. The AMOG, though, as is shown in the very simple depiction on the right here, it passes through the Gulf Stream here in this region, but the Gulf Stream itself transports about 90 Sverdrup, that's 90 million cubic square meters of water per second. And the AMOG is only 15 to 20 of that. So it's a smaller part of the Gulf Stream, but it is the bigger part for the heat transport, because the AMOG actually gives the heat off to the atmosphere in the high northern latitudes. The water gets cold there, sinks down, and returns as a cold, deep current between 2,000 and 3,000 meters depth. And so it works like a heating system, whereas the wind-driven part of the Gulf Stream waters remain near the surface and return south at not much lower temperatures than they came north, so they don't leave behind much heat. So the AMOG is really the big player when it comes to heat transport. And it's part of a global thermohaline circulation, which thermohaline meaning driven by temperature and salinity differences, which together make up the density of ocean waters. And where the density is the highest, that's the so-called deep water formation regions shown in orange here. That's where the water sinks down to great depth and supplies the deep ocean with oxygen, for example. And that is happening in the Northern Atlantic and around Antarctica, but not in the North Pacific. The effect on temperature you can see, for example, with model simulations, a recent one by the colleagues from Holland, Van Westen et al., showing the difference between a world with and without AMOG. And without AMOG, the whole Northern Hemisphere would be significantly colder and the Southern Hemisphere warmer. In fact, as we showed many years ago with Georg Feulner, the main reason why the Northern Hemisphere today is warmer than the Southern Hemisphere is the AMOG. When you switch it off, the difference in temperature and mean temperature of the hemispheres basically goes away. You also see that there is a focus of the cooling after an AMOG shutdown in the region, kind of the northwest of Europe and the ocean outside there. The AMOC has been unstable in the past. I can't discuss it in great detail, but there have been, for example, these abrupt glacial climate changes, Dansgaard-Oeschger events, but also Heinrich events. And we have studied this mainly with Andrzej Garnopolski more than 20 years ago. Discussing that would be a whole separate talk, but we have seen during the last 100,000 years or so, we have often seen abrupt climate changes with a focus on the Northern Atlantic, which are strongly linked to instabilities in the Atlantic Ocean circulation. But now we are in a modern age of global warming in the Anthropocene. We have seen this increase in carbon dioxide, and as predicted, it is followed by an increase in global temperature by 1.2, probably closer to 1.3 degrees already. And when we look at the map of this modern global warming, it looked like this. This is a version with the Berkeley Earth data plotted by Sieg Hausfather. And you see practically the entire globe has warmed. Antarctica, we don't know from the 19th century for lack of data, but there is one region which has definitely cooled since the 19th century, and that is the Northern Atlantic, exactly that region where the AMOC delivers its heat. Here's a view of the same thing since the satellite data from the Copernicus Climate Data Service, showing in much greater detail this so-called cold blob in the Northern Atlantic in the trend, in this case, since 1993. But it's not only the sea surface temperatures which show this phenomenon, but also the ocean heat content of the top 2,000 meters. A paper by Cheng et al. Here shows that where you see that down to 2,000 meters, the Northern Atlantic is a region of big heat content reduction, whilst the rest of the globe has basically been warming. This cold blob was predicted for a long time as a result of global warming by climate models. In several IPCC reports, you see different pictures of predictions for the future which show this, including this diagram is from the latest IPCC report. And I actually, on my hard disk, I have a big collection of images like that, maps which models predicting this North Atlantic cooling as a result of a slowdown of the AMOC. But if you look at the latest IPCC report, you see that they have already in the summary for policymakers a comparison between the observed change after 1 degree global warming and the simulated change. And observed is this cold blob in the Northern Atlantic, but it is greatly underestimated in the simulations. I'll come back to that underestimation a bit later, but want to note that the previous model generation, the CMIP5 models, actually did predict a cold blob in the model mean in the historic runs until today. So this is kind of a feature of the latest models, whereas earlier models included it. Now, we looked at this in more detail together with Levke Cesar by using the GFDL's coupled global climate model, the CM2.6 model, which has a very beautiful ocean resolution and a very good depiction of the ocean circulation. You can see here the Gulf Stream in red coming up the American coast, leaving it at Cap Hatteras, then, forming these meanders. By the way, also shows that these simplified images where it looks like it's all like a straight river are of course not true. There is turbulence superimposed on these large-scale motions. Now, when you use this model and double the CO2 in this model, then you get this pattern of sea surface temperature change, where I need to point out that it has been normalized here. That means the sea surface temperature trend shown here has been divided by the global mean sea surface temperature trend to kind of take out the global warming effect and isolate just the other effects that are not a global mean change. So everything which is white has the same warming as the global mean, and everything which is blue here has warmed less than the global mean or cooled indeed. and everything that is orange, red has warmed a lot more than the global average sea surface temperature. And now you see not only this cold blob in the Northern Atlantic, but you see also a region of excessive warming along the North American coast. And it turns out this also is an indicator of a change in the AMOC. The theory behind this was beautifully laid out by Rong Zhang in a paper in 2008, where she actually, in this case, looked at a strengthening of the AMOC. That's why the colors are reversed. The sign of this change is reversed compared to what we're looking now. It was more a theoretical study, but she actually showed that if you slow down the AMOC, the Gulf Stream moves closer to the American coast because of a question of vorticity conservation on a rotating sphere applied to where the deep branch of the AMOC crosses underneath the Gulf Stream. So it's a bit involved to explain this, so I won't explain any more detail of that, but it's understood physics, it's vorticity conservation, which means if the AMOC slows, the Gulf Stream moves closer inshore. And if you look at the CM 2.6 climate model here, you can see very clearly how the Gulf Stream has moved closer inshore, because that red-orange area along the American coast, to the south of it, you have a blue area where it has cooled because the Gulf Stream has moved away from it and it has moved north. And that's why in the northern part here, it got warmer. Now, Levke in her PhD thesis looked at all the sea surface temperature data from the 19th century and computed the trend since 1870 up to 2016. And it looks like this. And I think you can clearly see what we call the fingerprint in this paper of an AMOC slowdown, including that cold blob around the southern part of Greenland and the warm part of the fingerprint along the American coast. Now, this is a very fuzzy picture because it's shipboard measurements and you don't have that everywhere, every year since 1870, obviously. So there's some space-time averaging involved. But if you look at the, before I come to that next slide, we calibrated the strength of this trend pattern with the help of the CMIP5 climate models, and it would be consistent with about 15% weakening of the AMOC in the historic period. Now, to see the pattern in higher resolution, we can turn to the satellite data. This is a trend from the Copernicus satellite data again, and you very clearly see a cold blob, obviously, but also the warming along the American coast, a cooler bit to the south of that warming stripe there, which indicates that there is actually a northward shift of the Gulf Stream happening there, as deduced from the sea surface temperature trend. Now, the first paper that I know of that actually linked this observed sea surface temperature pattern to a slowdown of the AMOC is from my colleagues Dima and Lohmann from Alfred Wegener Institute in Bremerhaven, who published this paper with a pattern analysis, an EOF analysis of sea surface temperature changes, and they found this correlation pattern between South Atlantic and North Atlantic, and the North Atlantic part of that is shown here on the left, and the corresponding time series is on the right, because the time series kind of goes down. It means the pattern part that is red there is cooling now, and the pattern that is blue there is warming. So it's kind of, the colors are reversed, but it's showing the same thing, of course, as I showed in the previous images. And they already concluded the global conveyor, as it was called back then, refers to the AMOC, has been weakening since the late 1930s. There was further investigations by the Dutch colleagues of this, confirming basically that this pattern that we see in the sea surface temperature, that cold blob, is actually, they called it a warming hole here in the title of their paper, is linked to a slowdown of the AMOC. And it doesn't appear in the radiatively forcing fingerprints of the models. It's only related to the AMOC. We can also look at this with a different type of data yet again, the reanalysis data, the ERA 5 data. In this case, this data set starts in 1940. You see the same thing again. You see beautifully the cold blob. You see the warm part of that fingerprint pattern. And with the ERA 5 data, we can also look at the question, could this be caused, like the cold blob, could the cold blob be caused by increasing heat loss through the ocean surface? My bachelor student, Jan Jędrkowiak, has just done that. And the opposite is true. The surface heat flux trend means there is less heat loss at the ocean surface in this region. So the cold blob is not caused by losing more heat there. Rather, it is caused by less heat being transported to that region and therefore also less being lost through the ocean surface. And the same thing applies with reversed sign to the warm part of the fingerprint. That's also not caused because there is less heat loss there. There's now more heat loss than there used to be because the Gulf Stream brings more heat into that part. If you have this pattern, this is for temperature, but the AMOC also transports salt, of course. The AMOC is the reason why the Northern Atlantic is so salty that it can form deep water there, other than the North Pacific, which is lacking PMOC, also it doesn't exist there. And so if you weaken the AMOC, you would expect a freshening in the cold blob area and increased salinity from the Gulf Stream in the warm part of the fingerprint. Now, this is what the salinity trend looks like. You do have a fresh blob also in the area where you have the cold blob, and you have increasing salinity where you also have increasing warmth from the northward shift of the Gulf Stream. The time series for this pattern is shown on the right. You can see it's reaching record levels. And in fact, this paper by Penny Holliday and colleagues shows that in the Iceland Basin, there is now the lowest salinity in 120 years of data. That is fully consistent with what we expect from a slowdown of the AMOC. And actually, the ECMWF reanalysis product also has an Atlantic heat transport reconstruction as a function of latitude. And you can see that across all latitudes from the south to the high north, the heat transport has been declining since 1975. There's a caveat there that the decadal variability and long-term trends for this product have not been validated. So we have to see and know more about exactly how this product is produced. But let's at this point say with some caveat, but it is consistent also with the idea that the AMOC has been slowing down. It's what we expect also based on the CMIP5 models. I mentioned them already. This is from the Lefke's paper from 2018, where we looked at the historic runs in the CMIP5 models, so the last 100 something years in the models up to now, and the correlation between how strongly is there a cold blob and how much has the AMOC weakened in these models. There's a very high correlation. The AMOC weakening shows big differences between models. Models basically don't agree very well on how much weakening there will be, etc. But the correlation coefficient is 0.95 between the AMOC weakening in the models and the intensity of that northern cooling in the models. For the CMIP6 models, a more sophisticated correlation analysis has been done by Latif and colleagues in 2022. And so it's a joint correlation pattern between the AMOC stream function seen on the right-hand panel and the sea surface temperature change pattern in the left panel. And you clearly see both the cold part of this pattern and of the fingerprint and the warm part on the American coast of the fingerprint pattern clearly correlating with the AMOC strength in the CMIP6 models. Even though those models in the historic runs, they underestimate the strength of that, so they don't actually have a net cooling in the cold blob area on model mean, but the pattern correlation clearly supports the fact that it is linked to the AMOC. And so if these models underestimate the cold blob, they're probably underestimating the AMOC slowing. There's further corroborating data. This is just since 2001, but since 2001 is also a time period where the AMOC has slowed, and the 3D data showing that the Gulf Stream has actually moved inshore during this time interval. There's also, it has been shown by Chris Peakach in 2020 that the Florida current, which is the southern part of the Gulf Stream, has actually slowed down by 1.7 Sverdrup, which is approximately consistent with what we got from the cold blob. And he also in this paper does a correlation, or rather a heat budget calculation, I should say, saying this amount of slowing of the AMOC would explain that cold blob. And of course, we can't be sure whether Florida current slowing is AMOC or is part of the wind-driven part of the Gulf Stream. We don't know that, but it is at least consistent. And there's also, for the last 4 decades, another paper showing a robust weakening of the Gulf Stream. We can also turn to paleoclimate data because there are different published proxy reconstructions of AMOC strength. Of course, with all the uncertainties and caveats of paleoclimate proxy data, they are obviously proxies and not direct data, but they tend to all, with very different methods, agree that the AMOC has been stable for about 1,000 years, and then in the last 150 years or so has gone down and is now weaker than any time in at least the last millennium. And you can discuss whether at the end of this, how well do the proxy data that go nearly up to the present, many don't, of course, stop 100 years ago, because that's what sediment data tend to do. How consistent are they for recent periods with the more modern reconstructions? On the top, you see the direct AMOC measurements at 26 North from the RAPID project. You see below that 2 reconstruction based on other modern observational data. Then the blue curve is the Caesar et al. Reconstruction of AMOC based on that cold blob, and then 2 sediment data reconstructions. And I would say, of course, they don't agree in every detail. That's not what you expect, obviously, but by and large, they are not inconsistent. Now, let me just mention 2 effects of the already existing cold blob out in the Atlantic on our weather. There's one nice study by Aurélie Duchesse, already going back to 2016, and it is a bit counterintuitive to those who maybe have watched the movie The Day After Tomorrow and think, oh, well, this AMOC slowdown would make Europe cold. It actually leads to more heat waves. At this stage, of course, AMOC collapse is a different story I show you at the end, but at this stage of 15% weakening and a cold blob out in the Atlantic, what does it do? It encourages a low pressure above the cold region. And then, as shown in the red arrow there, of course, the air tries to go around the south of that low pressure, and then it enters Europe from the southwest. And if we have winds coming into Europe from a southerly direction, that brings warm air. And yeah, that was nicely demonstrated by this Duchesse paper. And more recent one by Efi Rusi, which probably is in the audience somewhere, shows that the heat wave intensity in Europe has increased 4 times faster than on average in those mid-latitude regions. And this is also in the paper linked, at least potentially, to the influence of the cold blob out there on the circulation pattern. And as another example of the impacts of that is this modeling paper by Jackson et al., suggesting that it leads to increased wind storms into Europe. So now let me come to the second part of my presentation, which is about the question of tipping points. And I first want to talk about what is a tipping point. Think of a ball sitting in this bowl there. It's a stable equilibrium. So the ball would just sit there. Now there's this person which can push it a little bit to the right, then it would roll back to its former stable equilibrium, unless, of course, this person pushes it beyond that point shown by the arrow. And that point is a tipping point, because from then on, the system evolves further into a different state without being pushed further, just by itself, by internal feedback. That's how the tipping point is defined. And that this thing could happen with climate was already actually suggested by Stommel 1961 in his paper, but a very powerful argument for this was put forth by Wally Broker, the late Wally Broker, in this Nature commentary in 1987, titled Unpleasant Surprises in the Greenhouse ? Where he points to the fact that paleoclimatic data tend to show rather erratic, abrupt changes in climate, quite unlike what the smooth climate models were suggesting at the time. In particular, in relation to ocean circulation. Of course, Wally was the one who talked about the great conveyor belt. He coined that term for the thermohaline circulation and studied its instabilities. And in his commentary, he writes that we play Russian roulette with climate and no one knows what lies in the active chamber of the gun. So he is pointing very strongly to a risk there that climate change may not be as smooth as we expect. There has been now a lot of progress, of course, since Wally Broker's article. And one of the highlights is at the end of last year, the Global Tipping Points report, 500-page report by more than 200 researchers from over 90 organizations in 26 countries, which has as a headline conclusion that harmful tipping points in the natural world pose some of the gravest threats faced by humanity. Their triggering will severely damage our planet's life support systems and threaten the stability of our societies. So that is at stake. And the IPCC synthesis report last year also pointed to risks associated with large-scale singular events or tipping points transition to high risk between 1.5 and 2.5 degree global warming. So beyond 1.5, we start to move into the high risk area. The IPCC says below 1.5, we're in a moderate risk area. So it's not like there is not already a risk at the amount of warming that we have now. And indeed, we may well already have crossed the tipping point of the West Antarctic ice sheet. There is a strong discussion on this issue in the literature. Now, returning to specifically the AMOC, there are actually two kinds of tipping points linked to the AMOC. One is that shutdown risk. And this is from a review paper in Science 2022, which looks at all the world's climate tipping points. And so it has these two lines there in the table, one for the AMOC collapse, but above that is one for a regional constrained convection collapse in the subpolar Gyre region, the Labrador-Ermanger seas. That's shown in this diagram here. So this concerns the deep water formation sites to the south of Iceland, which actually in a surprising large number of models, like 35% of the climate models that have a good simulation of this region, of the salinity temperature structure, show a shutdown of the convection there already by about 2040. And that is not as bad as a total AMOC collapse, because you have the northern convection sites north of Iceland still going, but it would already have massive impacts on society. So I think this is a greatly underrated and under discussed risk that we need to pay more attention to. I can't do that in this talk, unfortunately, because of time constraints. So I just want to flag this here, but then now continue to talk about the tipping point for the full shutdown of the AMOC. And this was first suggested in 1961 in a paper by a famous American oceanographer, Henry Stommel. And this was a very simple model which illustrated the functioning of the salt transport feedback. I already mentioned that the Northern Atlantic is salty because the AMOC is transporting not only heat, but also relatively salty water into that Northern Atlantic. And so you can say the water there is salty because there is an AMOC, and the salt makes it dense enough to sink, so the salt actually drives the AMOC. So we can say the Northern Atlantic is salty because of the AMOC, and there is an AMOC because it is so salty. So it's a self-amplifying feedback, and that would work the other way around. If you dilute the saltiness of the Northern Atlantic, you come to a point where the AMOC becomes so weak that amplifies the loss of salinity there, and at some point it just breaks down. There are basically two equations. If you combine them, you get a quadratic solution. That's the analytical solution for Stommel's box model, and it has this clear bifurcation point. So if you are in this middle regime, in the bistable regime, you can have either an AMOC or not an AMOC, depending on the initial condition. If you start without AMOC, it will remain there. If you start with an AMOC, the AMOC will also remain. So that's why it's bistable. It has two stable states. Now, if you add more and more fresh water that is moving to the right on this graph, then you hit this bifurcation point where the curve bends back on itself and you fall off the cliff, and you cannot sustain the AMOC beyond that point. It will come into a complete shutdown. Now, there is a question mark here where the present climate is in this diagram. In this picture, I put it in the bistable regime. Many models want to have it on the left in the monostable regime, and I'll get back to that point later. I just want to flag this here, that this is an important point of discussion. Where actually are the climate models, and is that realistic? Now, with modern warming, of course, we're not following the equilibrium line, because we're not only changing the freshwater input, we're also changing the temperature, we're generally changing the climate, and also relatively quickly. So we don't necessarily stay on the equilibrium path. We might follow something like the blue curve here. And then for that situation, the tipping point would be when that arrow crosses the dashed line. That is an unstable equilibrium, like the ball sitting on the cusp of a hill. And so when you go beyond that point, you get into the area of where you are attracted to the off state of the AMOC, and that would mean self-amplifying feedback will turn the AMOC off at this point. Now, that's a simple box model. You want to test that, of course, in fully three-dimensional circulation models, etc. This is what I worked on actually with Jürgen Willebrand in Kiel in the 90s. And I published this paper where I used the again, GFDL ocean circulation model in a coarse resolution version. And if you want to calculate 1 point on the equilibrium curve, you have to run the model for several thousand years. It's very computationally expensive, certainly was in the 90s. And so what you can do is you can very slowly dial up the freshwater input until you reach the tipping point. So tracing that equilibrium line. And that is what I did with that 3D ocean circulation model in the orange line here. So from the top AMOC on state or present climate, you move to the right, you dial up the freshwater input, and then because you do it in a finite time, not infinitely slowly, you don't quite follow the equilibrium curve, you overshoot the tipping point a little bit, but basically that is the point where you don't even need to dial up the freshwater any further. The AMOC will die there when it's beyond that tipping point. The black line, by the way, shows when I do the same slow tracing experiment with Stommel's box model, and it's basically exactly matched by the three-dimensional ocean circulation model, demonstrating that this quadratic stability diagram applies also to a fully 3D GFDL ocean circulation model. Then you can move to the left again. Then at some point, the AMOC restarts again. And that is called a hysteresis experiment, because a physicist would call that hysteresis behavior if on the back trace you follow a different path compared to the trace to the right. And this hysteresis experiment to find the tipping point has been done with many models. In 2005, we published a model intercomparison study of that, showing that basically, as far as I know, every single model that has been tested so far with such a hysteresis experiment has found the bistable regime and the tipping point, but the models disagree very much where on the stability diagram is the present climate. So that is a big uncertainty. Now, recently, Van Westen and I have done this full hysteresis experiment with a modern coupled global climate model. This is a horrendously expensive experiment. It took 6 months in a supercomputer to run this. And because you have to dial up the freshwater very, very slowly, moving to the right here along the black curve until you find the tipping point where the arrow is. From then on, the internal dynamics, internal feedback takes over and the AMOC collapses. And then you dial the freshwater input back again. And then at some point it starts again. So you have this big hysteresis behavior. Now, the present climate, the initial condition is to the left of where it restarts. So in this model, the AMOC is in the monostable regime, very far from the tipping point. That's why you need to add so much fresh water to reach the tipping point. But that does not mean that the real climate is so far away from the tipping point. Because there is a whole part of the literature arguing that most modern climate models are actually unrealistic in this respect. Already kind of looking back at the early parts of my career in '96, I suggested a diagnostic for that, how you could find out whether the models are in a bistable or monostable regime, and also look at this in observational data. And it's based on the idea that the AMOG, when it enters the Atlantic and the South Atlantic, it kind of gathers all the areas of net evaporation, net precipitation, all the river runoff that goes in, fresh water coming from the Arctic perhaps. And then at the bottom, it goes out again. And the big question would be whether the salinity here in the northward branch of the AMOG near the surface is greater or smaller than the outflow at the bottom here. And now we're talking here at about 30 degrees south. So I argued that the freshwater transport by the overturning circulation at 30 south should tell us whether the AMOG exports or imports freshwater. And so if the AMOG removes freshwater, then a shutdown would lead to a freshwater accumulation, and that would mean you're in that bistable regime. And in that case, yeah, it will be in the bistable state. Observations suggest that is the case. We have big uncertainties about the rainfall patterns and evaporation and all the freshwater budget at the surface, but we can actually measure salinities in the ocean very accurately. And so just by measuring salinity at 30 south, there are a number of papers on this. They suggest that the AMOG is exporting freshwater, and so it's in the bistable state and not in the monostable state. But the problem is that most models are in the monostable state, much further away from the tipping point, like that model of Van Westen et al. That I just showed, the latest hysteresis experiment. And so that would actually argue the models are too stable compared to what the observations suggest. The observations say we are much closer to the tipping point than the models would have it. There's another way of testing this. Very nice paper by Liu et al. 2017, where they looked at a climate model and found, okay, the salinity in the Atlantic is not looking very realistic. Let's fix it by a nudging term. You can nudge salinities towards observations. Of course, that kind of is not physical. So in some sense, it's questionable, but at least you end up with a model that has a much more realistic salinity distribution. And when they subjected that model to a standard CO2 doubling scenario, that's the orange line, the AMOG collapsed. But the model with the unrealistic salinity, the original version, it did not collapse. That is, again, a confirmation that AMOG and climate models tends to be too stable. Now, there is another type of study that can be done to look at the proximity to a tipping point, and that is the so-called early warning signal studies or critical slowing down. This is borrowed from nonlinear physics. Basically, it's not an invention by climate scientists. And the principle is quite easy to understand. If you have a ball sitting in this bowl here, but there is some random variability. So the ball wiggles around here by random noise. It will stay in this bowl. But when the background climate changes, so to speak, so the background stability curve changes here due to climate change in our case, then this the hump separating the two different stable states gets lower. The slope here gets lower. So if you wiggle it around, it will take longer to roll back to its former equilibrium state. And that's what's called critical slowing down. So it takes longer. That's why it's called slowing down. The autocorrelation increases, and that would indicate that you are getting closer to a tipping point, which is crossed then when you have the last state there. And I know of at least 4 studies that have done that. The first one by my colleague Niklas Börs. And he looked at 8 different observational data sets, which he took as proxies for AMOG variability, 4 temperature curves shown in the bottom left there, 4 salinity indicators shown at the bottom right there. And he calculated this stability indicator, which hits the tipping point when the zero is reached here. So when these wiggly lines reach zero here, that's where the tipping point is. Now, it's a bit scary that out of these four lines, three of them reach that point before 2020, and the salinity-based lines here, two of the four reach it even before 2020. And the conclusion that he drew in this paper is that there is strong evidence that the AMOC is indeed approaching a critical bifurcation-induced transition. Then there's a very interesting study, well, very interesting to me because I do a lot of paleoclimate research, by Michel et al. 2022, where they took a whole number of proxy data from the locations shown on the map here. So in this case, it's not marine data, it is land-based data, but they look at Atlantic multi-decadal variability in these data because you can see the climate variability caused by AMOC variations, then especially in Europe and into Asia. And they calculated the autocorrelation coefficient of the multi-decadal variability and diagnosed the critical slowing down here. And these are data going back 1,000 years. So, and something unprecedented happens in the last 100 years in these data, which they identified as the AMV, Atlantic multi-decadal variability, linked to the AMOC, may now be approaching a tipping point after which the Atlantic current system might undergo a critical transition. And there, of course, there are newspaper headlines about this. Two more papers, the one by Peter Ditlevsen, who's also sitting in the first row here. Hi, Peter. And his sister Susanne. And then the Dutch group in Utrecht recently made headlines with a study on a physics-based early warning signal. Now, I'm coming to a close almost, so let me quickly look at some of the impacts if there were a shutdown. Now, the Dutch group has done this model, which already in the beginning I showed a plot of showing the world with and without AMOC, but no CO2 increase. It's just the difference between with and without AMOC. And the cooling, especially what you get in winter in Europe, is quite horrendous. So in Norway, so you have like more than 20 degrees Celsius cooling in, in climate, not just one weather event, a mean temperature for February. And that happens all in 1 century. So they're talking about here the trend per century. So like 20, 30 degrees per century is 2 or 3 degrees per decade. That shows that within a decade, you can get a catastrophic climate change there in case the AMOC starts to shut down. Now that was without CO2, but this study by Liu et al. That I already mentioned, where the AMOC shut down in a CO2 doubling experiment, can be used to look at the combination of double CO2 world, but without AMOC. And then you get a temperature change pattern shown in the top image there. Most of the world has warmed, obviously, because of the CO2 doubling, but over the Northern Atlantic and into Great Britain, Scandinavia, you actually get a colder climate. And it's not confined to that. Because of that change in the temperature difference between the hemispheres, you also get a shift in the tropical rainfall belts. That is something we also see in paleoclimatic data when there are Heinrich events, breakdowns in the AMOC in the past, that the tropical rainfall shifts because it tends to be at the thermal equator where it's warmest, and now that's north of the geographic equator, but it will kind of move to the south. That's why you have these strange dipole patterns here of rainfall bands. So you have a reduction in rainfall here in the north of the equator and an increase south of the equator, or at the equator, I should say, which has a lot of impacts on like the rainfall not being where the rainforests are anymore, agricultural impacts, and so on. So this is also one of the very important long-distance impacts of an AMOC change. And I sometimes get asked by especially German journalists whether it wouldn't be a good thing with global warming if the AMOC shuts down, because that cooling would compensate the CO2 warming. That is a bit of an illusion, because obviously the patterns are totally different. And even where the pure average climatological temperature effect would just compensate, so just between the blue and red areas there, you have first of all, a much larger gradient of temperature between Southern Europe and Northern Europe. And of course, that's just an average. There's weather variability. So you get cold air outbreaks with much colder cold air coming in from Norway, say, and you have warm air coming from Spain, which is much warmer than we used to. So this is not going to compensate. This is going to be a climate that will give us unprecedented weather extremes. And another impact is the one on sea level. If you shut down the AMOC, that's a study with Anders Levermann already done in 2005, showing how the sea level would change after an AMOC shutdown. And that's in addition to a global sea level change due to global warming. So in the Northern Hemisphere, you can get up to 1 meter extra additional sea level rise from an AMOC shutdown for dynamical reasons, because the sea surface, oceanographers know that, is obviously not flat. It is tilted depending on the currents. And that's why you get these dynamical sea level changes when the AMOC shuts down. And so this is bad news for many Northern Hemisphere coastal areas in terms of a lot of additional sea level rise happening then relatively quickly. So I come to my conclusions. And the first one is that I'm convinced that the AMOC is weakening because there's so many multiple lines of evidence all consistently pointing in the same direction. It is superimposed by large interdecadal variability and so on. That's clear, but I think the very long-term trend is maybe smaller than the decadal variability, but there is strong evidence that it is real. We know it has a tipping point since Stommel suggested in the 61. It has been confirmed and tested in many models, and they always found this. If they looked for it, there is some misunderstanding that people dump a lot of fresh water, get a shutdown of the AMOC, and when they remove the fresh water again, the AMOC restarts again. That is not an experiment that shows there is no tipping point. It just shows that you're in the monostable regime, far away from the tipping point with that model, probably unrealistically so. You have to do a full hysteresis experiment to see whether there is a bistable regime and a tipping point. The big thing is, because the models really disagree on this, it is still very uncertain how close it is. We have these early warning studies, but they also have large uncertainty ranges. And I think the conclusion is that they give us a warning that the tipping point could be closer, but before we get a definite warning, it will be too late. We will have crossed the tipping point. So we know the risk is larger than we have thought, also larger than I think the last IPCC report suggested, on the basis of models that are too stable probably, and before a lot of these early warning signal studies were published. And because of the uncertainty, we won't get a definite news in time to stop it. So the precautionary principle should apply. Given the horrendous consequences if the AMOC shuts down, we should really minimize this risk as much as we can. It's, I think, already too big for comfort, and it's even bigger than we thought. And we should do everything with high priority to minimize it. And that means nothing else than all countries already promised, namely trying to limit warming to 1.5 degrees C, as in the Paris Climate Agreement. With that, I come to the close. And if you want to read more, last week, as it happens, a feature article in Oceanography has been published where I describe much of what I have covered in this lecture. And now I look forward to a discussion and questions. Thank you very much for listening.